Today we are going to be talking some more about statistics, but today we're going to do something a little bit different than we've done in the past couple lessons. In the past couple lessons we've been doing comparative statistics, where we're given two different types of data and comparing them, making an equation that was either a linear equation if they were following a straight line pattern, or a quadratic equation if they were following a curved or more like a parabola pattern. One of the dangers of comparative statistics is when we see a relationship between data, we often want to assume that means that one of the pieces of data is causing the other one to happen. Okay? So for example, if I took a large portion of society and asked them for two pieces of data, their shoe size and a score on a reading test, I would likely find that the larger the shoe size, the higher the reading score. I sincerely doubt that having large feet means that you're a better reader. So what might actually be happening there? The age, right? If I took a large portion of society, children to adults, adults should be able to read better than children and should also have larger feet than children. So when we see two variables that do in fact have a relationship, it doesn't necessarily mean that one of them caused the other one to happen. Sometimes people will intentionally mislead you with this. A lot of times in news articles or other media sources, they might give you a relationship that shows that two particular things do in fact have a relationship. That is, one of them increases, the other one increases as well. But that doesn't mean that one of them is causing the other one to increase necessarily, which is often a jump that they want to take. So it became really popular a few years back that people got a belief that if you would play classical music for a baby while it was still in the womb, it would have a higher IQ. Possibly. My theory on that is that the parents that are more likely to play classical music for their baby are probably parents that themselves have a higher education and will value education more for their children, which will help their children progress in education. So that there's this kind of hidden thing happening behind the scenes that one of them is not necessarily causing. We call that a lurking variable, that there's something else kind of behind everything that's causing everything to happen. Today, we're not going to be talking about comparative statistics, but rather one statistics, where we just have one list, and we want to find the middle or the central tendency and the spread of the data, or the dispersion. There are a few different measures we can use for this. For the middle, we can say that it is the mean or the average of the data, which is all the data added together divided by how many there are, and that can tell us a middle value. Or the median, which is, if we line up all the data in order, the actual middle value. Okay, so line them all up in order, and what number is right in the middle of that list is the median. Or the mode is the one that happens the most frequently, or shows up times. If I gave a test to all of my students and everybody pretty much did right about the same, like B plus-ish, except for one person, they totally bombed it. If I took the average or the mean, add them all up, divide by how many there are, that one person's score can shift the whole average sometimes pretty significantly, depending on how far away it is from what maybe the true middle of the data is. As opposed to, if I reported the median and lined them all up and found the middle number, that is not so affected by what we call an outlier, an extreme high or an extreme low piece of data. So people can choose to tell you what kind of middle they want to maybe get their point across. You actually have a homework problem that's about that. There's actually a whole book that's written called How to Lie with Statistics. It's really easy to make people believe what you want them to believe when you use numbers. People have a lot of faith in numbers. They feel like something's solid. But the way we interpret numbers and the way we display numbers, we can intentionally or unintentionally mislead people. Graphs are a really easy way to mislead people into believing something. So the way we scale our axes if I wanted to show that four different groups, we'll say, four different age groups of people are all right about the same level on something, I could create a scaling that would show 4 bars that are all really close to each other. If I wanted to say that one particular age group was much higher or much lower than another one, I could just adjust that scaling and exaggerate the differences and say, hey, look, this one is tons higher, where it's exactly the same data, and it's just the way it's displayed. So all this to say, just be careful when you see numbers and data and news articles or media sources that you think about what are the numbers actually saying, not what does the author want me to believe about these numbers. It's really easy to mislead people. My college statistics professor said that every time he had been called for jury duty, when they would ask him what his profession was, he would say, I'm a professor of statistics, specifically, instead of saying I'm a math professor, because typically in a court case, one or both sides are going to try to throw some data out there and maybe want the jury to believe it in one particular way. And knowing that he would kind of know their tricks, he was never actually selected for a jury. So that was kind of his way of always getting out of being in jury duty. The other side would want him, but the side that was maybe going to deceive would dismiss him. Yeah. Because you get to, as a lawyer, you get to dismiss some people for, you don't even have to say why, you can just say, I don't want them to be on my jury. Like 4 or 5. And so he would always get dismissed by one side or the other. So to enter our data today, we're going to enter it in the same place that we have been. So we're going to go to Stat, Edit. We're going to clear the data that we have in there from yesterday. And we're going to enter our new data. Today, though, we're just going to be entering one list of data as opposed to 2 lists of data. So we're going to go to the same place we went to yesterday to enter data, but today we're just going to be entering it all into L1 instead of yesterday we had stuff for L1 and L2. Then we're going to do some calculations like we did yesterday, going to Stat and over to Calculate. In the past couple days, we've been choosing regressions, which is how we compare 2 pieces of data. Today, instead of comparing 2 pieces of data, we only have one type of data to deal with. So we're going to choose choice 1 that says 1 variable statistics. There's only one type of statistics here. So 1 variable statistics, and hit enter on that.
So we just put all those numbers in L1.
All the numbers into L1, yep. And we get a lot of data pieces here. Most of these we're actually not really going to care about. Some of them we will care now. Some of them we'll come back to. The very first one, the X with the little bar above it, mathematicians being super creative, we call it X bar. But that X with the little bar above it is the symbol for the mean, or the average. So that first number, 8 1/3, is our mean, or our average. So
after we go to bars, we press statistics, then we press
we don't go to bars. We go into statistics and over to calculate, and then 1 variable statistics.
Wait, which ones?
So the first one so far, that X with the bar above it, is our mean. So our mean is 8.3 repeating, or 8 1/3. The second piece of data there, that little like pointy E sideways M thing, we talked about that in the last chapter. What does that mean? It's the sigma, and it means the sum of all the data. So that sigma X is what we would get if we could add up all the data. We don't really care about that for anything, but just kind of referencing back to there's a symbol that we saw before, and here's doing the same thing. Then there's the sum of everything squared. That's for a different purpose. We don't care about that. The other stuff we'll come back to talking about. N equals 6 tells us how many data points we have. So we entered 6 pieces of data.
Can you send Sam Showalter down to the office?
Yep.
Thanks.
And we can scroll down and it gives us even more information there. Of those 5, the only one we care about right now is the one that says MED for median, which is 9. So for question number 1, we were asked to find the mean, which is that X bar third. We're asked to find the median, which is 9. And we're asked to find the mode. The mode is the most common piece of data. The calculator will not give you the mode. So then you just need to look at the list and see which one happens the most. So for number 1, it's 9. Scroll down. It gives you more.
Wait, what's Q1?
We haven't talked about Q1.
Okay, which one?
So far, we just care about X bar, which is mean, and the median, MED. The mode, the calculator will not give you. It's just by looking at the list, the one that appears the most.
Is median is median like the middle from numerically, or how like the order would be?
Yeah, the median is the middle if they're in numerical order. So if they're in increasing order, then it's the exact middle. For this particular set of data, there are 6 values, and they are in order already. So if we kind of match up to find the middle, there isn't a middle number because it's even. So there's like 3 low numbers, 3 high numbers. If that happens, that you have an even set of data, the median is the average of the 2 middle numbers. Okay? For an odd set of data, and that is the median. If it's an even set of data, the median is the average of the 2 middle numbers.
Do we have to make sure that they're in order when we plug them in?
You do not. You do not need to put them in order in the calculator. The calculator will take care of what it needs to take care of.
What do we do for the mode if there's a tie of like things?
It is possible to have more than one mode. So if most of the data is occurring once, but then there are 2 things that occur twice, they are both the mode. We call that bimodal. Possible to have 3 modes. We call that trimodal. We could have 4 modes. But if all of the data occurs the same number of times, then there's no mode. So if everything just shows up once, there's no mode. If every piece of data showed up twice, there would be no mode. But if there is some of the data points that show up more than others, it is possible to have more than one mode.
What if all the data except for one number occur at the same amount of times?
Yeah, strange situation if everything occurred twice except one thing occurred once. And I guess technically you would say that all of them except for that one were the mode, but that's just kind of a strange thing. That would definitely be a case where the mode would not necessarily be a good measure of the middle. Let's go ahead and look at example 2. So we're going to go into Stat, Edit, and clear the information from problem 1 and put in the new numbers for problem 2.
So did you say that it doesn't matter what order we put them in?
It does not matter what order you enter them into the calculator. If they are in order or not in order, that doesn't matter. I'll actually show you a little bit later how you can get the calculator to put them in order for you. Once you've entered all your data, press Stat over to Calculate and choose that one variable statistics option, and then press Enter, and it gives us our new data, our new statistics about our data. X bar is the mean, so that's about 49.57, 49.6 is our mean or average. Yeah, 1 or 2. I'm not going to be real picky about that. As we scroll down then, we can find our median is 47. That's the middle number. Since there were 7 pieces of data here, there actually is a true middle. So that 47 is the true middle number of the data. For the mode, we can look through the list of data, and since this data is in order, it's easy to spot what one happens the most times. If it's not in order, it can be difficult to spot which one's happening the most times. But like I said, once we move a little bit further into the lesson, I'll show you how the calculator can actually put it in order for you. And that can make it easier to spot the mode. But on number 2, what is the mode? 47. So the mode there is 47. Happens the most times, at 2 times. Questions on mean, median, or mode? Okay, the next thing we're going to talk about is our measures of dispersion, or how spread out is the data. So this tells us, is our data kind of all clustered close together, or was there a pretty wide separation here? There are 2 ways that we measure dispersion. The first way is range. To find our range, we take the biggest data minus the smallest data. Biggest minus smallest gives us our range. The second way of measuring dispersion is called our standard deviation. And the formula for that is right next to question number 3 here, where it has that little O with the tail. That's actually a lowercase sigma. So that big capital sigma we used to mean the sum, we use that for our series. This is the lowercase. It looks like an O with little tail. And that's our symbol for standard deviation. What this formula says here is that I'm going to take x1, which means my first piece of data, and subtract x with the bar over it. What does that symbol mean? The mean. So I'm going to take each data point and subtract the average and then square it and add them all together. So take the first data, subtract the average, square it. And then take the second data, subtract the average, square it. And add all that up. Divide by n, which is how many data there are, and then take the square root of that whole thing. This is disgusting to have to do by hand. Thankfully, we don't have to do it by hand. But I do want you to know what this number means when your calculator pops out a number and we say that's our standard deviation. What is that telling us? What the standard deviation is doing is saying, on average, how far away is the data from the average? So it's taking each piece of data and saying, how far away is that from the middle, and then averaging that. So giving us the average distance of the data away from the middle. So the closer that standard deviation is to 0, the more clustered the data is together. If we get a really big standard deviation, that means that our data is really spread out. To have our calculator tell us about standard deviation and range, we're going to do the same thing. So edit, clear what we have in there, enter our new data for question 3. And go to the same place we've been going today, over to calculate, one variable statistics. In that list of information, we now see that little O with the tail on it, or the lowercase sigma there, is about 17.08, 17.1. That's our standard deviation. So on average, the data are about 17 away from the average.
So we don't have to do that.
Okay. No, we're not going to be doing it by hand. Doing it by hand is not a pleasant experience, especially if you have a large set of data. The S right above that sigma is a different formula that does basically the same thing as standard deviation. It's still a measure of dispersion, but we're going to stick with the sigma one. So that little O with the tail is what we want for our standard deviation. Question number 3 also asks for our range. Range is defined as biggest minus smallest. In this small list of data, and especially since they're in order, it's easy to see what the biggest and smallest are. But if they're not in order, we had a huge list of data, it could be difficult. But if we scroll down, it gives us the min and the max. And so to find our range, we just do max minus min. 60 minus 10 is 50. So our range of the data is 50.
So it says Q3 is 50.
That has nothing to do with it. No, that's a coincidence. So for range, we take the max minus the min.
What is Q3 and Q1 then?
I will tell you in just about 10 minutes. Not even, 5 maybe. For question number 4, I'm going to enter our stats again. Right. This list of data was not in order. So questions 1, 2, and 3, all the data was given to us in numerically increasing order. Question number 4 is not given to us in numerically increasing order. So we weren't asked to find a mode for this question, but if we were, it can be difficult if you have a large set of data that is not in order to find the mode there, because then you have to go, okay, well, there's 1 8, how many more 8s are there? Oh, okay, well, there's a 7, how many more 7s are there? And it can take a long time to try to find the mode if the data is not in order. The calculator can put the data in order for you. If you press your stat button, We get a choice that says sort A. That means sort ascending, so from the smallest to the biggest. So I'm going to choose that, the one that says sort A. And then I press the second in the 1 that says L1, so I'm telling it that I want it to sort L1, where I've been putting the data. I'll close it off and hit enter, and it just says it's done. Now if I go back in and look at that data, go back in to edit it, now it's in order from smallest to biggest. So you don't need to worry about rearranging it yourself. If you need your data in order for something, particularly to find the mode is really mostly where you would want it to be in order so that you could easily spot what's happening the most number of times. You can have the calculator sort it out for you so that it goes from smallest to biggest. They do a lot of stuff, don't they? It's a nice thing to have them.
It is.
Then I'm going to run the statistics on this. So I'm going to go over and calculate those one variable statistics. We get our standard deviation of about 143. Okay, that little O with the line, the sigma is our standard deviation there. And if I scroll down, I get my max is 1429 minus the min is 1012, and if I subtract those, that gives me my range is about 417. Okay. So standard deviation the calculator will give you. Range it will not give you, but it gives you your biggest and your smallest, and you can just subtract them. Okay? Questions? One more topic for timer. That's how long we've been recording. Our last topic for today is box and whisker plots. You may have seen these before in another math class. Box and whisker plots are kind of a strange thing to me because they seem really important to like high school math curriculum people. They're in every math textbook. They're on standardized tests that you take in high school, like MME, ACT, SAT, ACT, all of those kind of things. And they are on your standardized test score reports. So like when you get your ACT score report, there will be a box and whisker plot on there to kind of lined up with all the students who took it. Outside of that high school realm of high school math classes, high school textbooks, and high school standardized tests, I have never in my life seen a box and whisker plot. Ever. In any sort of article or statistical information, I've never seen them used. But apparently to somebody, they think it's a really important thing to know in high school. Thankfully, they're not like difficult, so it's not like a pain to have to learn this thing that you're probably honestly never going to see again once you leave high school.
And who invented them?
They are helpful, just nobody uses them. I don't know why nobody uses them, because they actually are helpful. They do show us some information about our data.
Maybe he's like the head of high school education in Michigan.
So I'm going to enter our data, same way we have been.
Formula thing in everybody's lives.
Everyone will use this.
Everyone will use this.
And I'm going to run the statistics the same way we've been running them. So enter my data, run my statistics the same way, and I'm going to scroll down. Those last 5 values that your calculator gives you are the 5 values that we need for a box and whisker plot. Those 5 numbers are called our 5-number summary. The minimum, Q1, median, Q3, and max. Okay, so the minimum is the smallest number. The maximum is the biggest number. We said the median is the middle number. So the median takes the data and splits it into 2 parts, the high and low part. Then the Q1 and the Q3 are the medians of those halves. So Q1 is the middle of the low part, and Q3 is the middle of the high part.
Where's Q2?
Q2 is the median. So that would be another name for the median. So Q stands for quartile. Quartile has that prefix in it, quart, which means 4. So it's like splitting the data into 4 groups. Okay. To draw a box and whisker plot from that data, what we're going to do is start with a number line. Scaling by whatever makes sense for the data in the question. So I'll just scale by 1 here, but you could count by tens or whatever would make sense for your number in the question. Above the minimum, I put a dot. Above the maximum, I put a dot. Above the quartiles, quartile 1, the median, and quartile 3, I put a line. I make a rectangle out of those lines and attach the dots to the rectangle. This creates a box and whisker plot. Okay? So the high and the low get dots. The quartiles and the median get lines, and from those we make a rectangle that has some tails on it. What the box and whisker plot shows us is if the data is skewed or heavier on one side than the other. So since everything in this graph seems to kind of be leaning towards the lower side, leaning towards 1, it's got a shorter tail over there. The median is closer over to that first quartile than the third quartile. What that means is there were more data on the lower end than there were on the higher end. That this data was actually lower than maybe what the mean would represent it being. Questions about how to create that?
So the smaller boxes where the more data is?
Yes. Yep. That wherever the smaller area is, that's where the data is more heavily clustered. So for question 6 then, we need to enter our data. Back in, set, edit, clear what we have, put in the new stuff. This data is not in order, so if we were asked to find a mode on this thing, we would probably want to put it in order to see what happens the most, although it's a small set of data, so you could probably just tell by looking at it. Then I'm going to run those one variable statistics and scroll down to the bottom to get my 5-number summary. Once again, we need a number line counting by whatever makes sense for the problem. So I'll count by ones here, but you could count by whatever you need to be able to adequately show the data. Now, something different about this one than the last one is that our values in our 5-number summary are not nice, clean integers. So in the last problem, when I put a dot, you could tell where I meant it to be. But if I just put a dot here, you can't necessarily tell what I mean that number to be. So if they are not nice, clean values, please label them. So that minimum is at 1.2. You get 1.7 for my Q1. 5.2 for my median. 8.5 is both the third quartile and the maximum. And this data is pretty well balanced. It maybe leans a little bit more towards the heavier side, but it's pretty well symmetrical. And that's it to creating the box and whisker plot. Questions on anything from today?